All right, welcome to The Explainer. Today, we are going way beyond just pixels. We're going to break down the past, the present, and yeah, the really profound future of teaching machines how to see.
So let's just jump right in with this really powerful idea. What if today's most advanced AI vision systems, the ones powering pretty much everything, are at their core blind? What if they're just seeing shadows on a wall and they think that flat projection is the real 3D world that you and I live in?
Okay, to really get our heads around that, we've got to make sure we're all on the same page. Let's start with a clear definition of what we're actually talking about here. So, at its heart, computer vision, or CV, as you'll hear it called, is really the science of trying to automate the just mind-boggling complexity of human sight. I mean, think about it. It's about taking the raw data from a camera, which is literally just a grid of numbers, and somehow translating that into a meaningful understanding of what's actually out there in the world. And here's what's so wild about where we are right now. These systems, they're absolute geniuses at pattern recognition. I mean, they can spot a cat, a car, even a cancer cell in a 2D picture with accuracy that blows human performance out of the water. But, and this is a huge but, their understanding is completely flat. It's totally based on those shadows, the pixels and the data they've been fed. They have zero grasp of the physical thing casting that shadow. And look, don't get me wrong, mastering these shadows has already changed our world in ways that are just unbelievable. This isn't some lab experiment. This is a massive engine driving the modern economy right now. I mean, think about it. It's in the cars that drive us, the hospitals that diagnose us, the stores we shop in, the factories that build our stuff. Computer vision is literally the foundation for huge leaps in automation and efficiency in, well, pretty much every industry you can think of. Okay, let's make this real. Take transportation. Tesla's autopilot, which uses only cameras, has safety stats that are pretty staggering. They suggest it's way safer than a regular human driver. We're talking about one crash for every 6.69 million miles driven. That's a lot of miles. Or how about retail? You've probably heard of Amazon's Just Walk Out tech. Well, it's allowed some of their stores to pull in an insane $2,700 in sales per square foot. To put that in perspective, that's up there with the most high-end, exclusive luxury brands on the planet. And it's all done by just getting rid of checkout lines with cameras. So it is absolutely crucial to understand how we got here. All of this amazing progress, it comes from one core strategy: scale. The philosophy for the last decade has been incredibly simple: bigger models, more data, hoovered up from the entire internet, and way more computing power. Just throw more at it. And you know what? For a long time, that bigger is better approach has worked like a charm. But that total reliance on just scaling up is starting to show some serious cracks in the foundation. We're beginning to see that what we've built is this powerful but incredibly fragile and almost illusory kind of intelligence. It's smart, but it doesn't really understand. The first huge problem is something researchers call brittleness, and it's exactly what it sounds like. These AIs can be absolute geniuses one second, perfectly spotting something, and then the very next second, they fail in the most bizarre, unpredictable ways. And it could be because of something as simple as a change in the lighting or a weird camera angle. And this fork problem really gets to the heart of it all. The AI doesn't know what a fork is. It doesn't know its shape or what it's for or that it's made of metal. Nope. All it's learned is that the pattern of pixels that we call a fork shows up really, really often next to the pattern of pixels we call a table. It's learned a statistical trick, not a real-world concept. And that leads us to this massive problem: a causal deficit. Basically, the models have no ability to understand cause and effect. They can't reason about why things happen. They don't get physics, they don't get gravity, they don't get basic common sense. Because all of that stuff is built on understanding that one thing causes another, and that's just not something you can learn from a flat, static picture. So this really deep weakness points to two totally different paths forward for teaching a machine to see. We can either keep doing what we're doing, having them passively look at a giant fixed photo album of the past, or we can build a whole new kind of machine, one that learns by actually doing things in the here and now. And that right there brings us to the solution. It's a huge, radical shift in thinking. We have to get AI out of the digital cave and into the real, physical world. This solution, which is really the next great frontier for the entire field, is called embodied AI. And it's a simple idea, really. It just means we give our AI vision systems a body, think a robot, so they can actually move around, touch things, and interact with the world around them. And this is how you fix that causal deficit we were talking about. See, an embodied AI can finally connect an abstract idea to a real physical experience. It's not going to learn what fragile means by seeing the word next to a million pictures of glass. No, it's going to learn by picking something up, dropping it, and watching it shatter. It learns physics by doing physics. That's a game changer. Now, the folks working on this see a pretty clear path forward, even if it's a bit speculative. The first step in the next few years is all about the basics, teaching a robot to understand a command like, hey, can you bring me the blue mug, and then actually do it. From there, it gets more advanced. We'll see agents that can experiment on their own, figure out how to use tools, and solve problems they've never seen before. And the long-term vision? A future where networks of these intelligent robots can collaborate on really complex goals all on their own. So this whole shift from just passively looking to actively participating, it completely changes the learning game. It kicks off a whole new era of what we can call active, self-directed perception. Think about it this way. Instead of us just spoon-feeding it a giant, unchanging dataset, an embodied agent gets to be its own teacher. If it doesn't know what's behind the couch, it can just go look. It can actively go out into the world and find the exact information it needs to learn more. It basically becomes its own little scientist, running experiments to understand the world. So when you boil it all down, it comes to this fundamental choice. Are we going to keep building systems that live in the cave, making them incredible experts on a static dataset of past shadows? Or are we going to move them into the workshop, letting them become true experts in the real, messy, dynamic world by discovering how things actually work for themselves? You see, this completely redefines the end goal for all of computer vision. It's not just about building a perfect digital camera eye anymore. The real prize is shaping an intelligent mind behind that eye, one that can actually act with purpose here in our world. And that brings us to the final and maybe most provocative thought of all. This shift from passive looking to active doing, it isn't just another technical upgrade. It could be the dawn of a completely new kind of intelligence on this planet. So the real question we're left with is this: what happens when the things we've built can finally leave the cave and start to shape the world right alongside us?